Welcome to our discussion of how to recover an interpretation from a truth tree. Let's begin by first recalling that an interpretation in sentential logic is simply just a truth value assignment. So let's think about how in sentential logic we might recover an interpretation from a truth tree. Let's consider the following set members. Suppose we have P, horseshoe, not Q, and R. That's a set member. And then we have Q or R, and that's a set member. And we also have P as our set member. And now we want to see whether there is an interpretation on which all these three sentences are true. And so we do that by, of course, constructing the truth tree and looking for a completed open branch. And here, perhaps the most efficient way to proceed is to decompose the first line first, because that leads to a closed branch right away, because the antecedent over here decomposes to not P. And then we have not Q and R over there. So this branch on the left closes. And line 4 comes from line 1 by horseshoe decomposition. Then we can decompose first the line number 4, that's going to stack and not branch, so we write down not Q, R, and check that off, and that comes from 4 by conjunction decomposition. And then finally, the only thing left to decompose is line number 2, so we check that one off and branch out like this, and we have Q on one side and R on the other. And on the left-hand side where we have the Q, this branch has the not Q, so that branch closes. So we have indeed a completed open branch. And from this completed open branch, we can recover an interpretation, or in this case, we could also call it a truth value assignment, on which all the members that are at the top of the tree, lines 1, 2, and 3, are true. And the way we do that is by simply reading up this completed open branch and looking at what in the textbook are called the literals. So in other words, all the sentences that are either atomic sentences or negation of atomic sentences, or if you want, the sentences that are not checked off. If we see an atomic sentence, then we say that that sentence has to be true in order for all three of the set members to be true. So for example, because R appears here, that means that R has to be true in order for all three sentences to be true. Not Q appears here. Now one way to think about this is to say that not Q has to be true in order for the three set members to be true. And if not Q has to be true, that means that Q has to be false. So put an F there. And P appears here. So again, since P appears, it means that P has to be true in order for the three sentences to be true. And indeed, if we look at these truth value assignments, we should be able to convince ourselves that on this truth value assignment, all three of these sentences are true. So for example, the first sentence has P as the antecedent, so the antecedent is going to be true because P is true. Then not Q is going to be true because Q is false, and R is going to be true. So we have a true antecedent and a true consequent, and that makes the sentence on line 1 true. The sentence on line 2 is going to be true because R is true. And finally, the sentence on line 3 is going to be true because P is true. So that's how we recover an interpretation in sentential logic when we have a completed open branch. And we can do something closely analogous to this, of course, in predicate logic. So let's look at a tree in predicate logic, and we're going to have just two sentences as our set members. First, our first sentence is going to be, there is an x, fx, and there is an x, fx, and gx, and that's going to be a set member. And then our second sentence is going to be, if for all x, f of x, then for all x, not g of x, and that's going to be a set member as well. Okay, very good. Using our usual strategies for decomposing sentences, we notice that each of the sentences on line 1 and 2 are both truth functional compounds. The main logical connective or the main logical operator in sentence 1 is this ampersand here. The main logical operator in sentence number 2 is the horseshoe. The ampersand decomposes with a stacking rule, whereas the horseshoe decomposes with a branching rule. So it's prudent to decompose line number 1 first by simply doing this, first writing there is an x f of x, and then there is an x f of x and g of x, and those both come from line 1 by conjunction decomposition, and we just check that off. Now, looking at this tree, we see that what we have now are two existentially quantified sentences on lines 3 and 4, and we have a truth functional compound. So here, perhaps the most prudent thing to do is to deal with existentially quantified sentences first. So on line 5, I can write f of a as coming from line 3 by existential decomposition. And I can introduce the constant a because it doesn't appear anywhere on the branch yet. And now, when I go to line 6 to decompose line 4, I cannot use the constant a because when I instantiate line 4, I have to instantiate to a new constant, a constant that is foreign to the branch. So I have to write maybe something like fb and gb. And it's just, again, following the convention of using our constants in alphabetical order. That comes from line 4 by existential decomposition. Now I can, of course, break that apart using a stacking rule for conjunction. So I can write FB, GB like that, and those come from 6 by conjunction decomposition. Now we have to deal with this truth functional compound here up on line 2. So we're going to check that off, and it's going to branch. And one branch is going to have the negation of the antecedent, which is going to be, it's not the case that for all x f of x. And the other branch has for all x not g of x. And that comes from line 2 by conditional decomposition. And here now I have two independent branches, so I can work on either one. Let's work on the left one first. I know that I can change that to there is an x not f of x, and that comes from 9 from negated universal quantifier decomposition. And I can now instantiate line number 10, but I have to instantiate it to a new constant, a constant that is foreign to the branch. Now on this branch, I already see the constant a and the constant b, so perhaps then it's prudent to go to c, so I check that off and I write down not fc. And that's all there is to decompose here on this branch. So this is indeed a completed open branch. Now, as it happens, on the other side, on the other branch, because this is a universally quantified sentence that says for any x not g of x, I can instantiate it to b, not gb, and that closes that branch. So line 12 comes from line 9 by universal decomposition. Okay, so we have one completed open branch, and what we want to do now is recover an interpretation on which all the sentences that are the set members, number 1 and number 2 up here, are true. If we proceeded just as we did in sentential logic, we might be tempted to simply make something like a truth table that would list these sentences FA, FB, GB, and FC. And that's not a bad idea. We might try to do this, FA, FB, GB, and then FC. And then we could say FC has to be false, and the other ones all have to be true. And when that happens, then these set members up here are both true. But unfortunately, when I do that, I don't specify the truth values for all the sentences, nor do I specify what universe of discourse I'm talking about. It looks like at the very least I need a universe of discourse with 3 things, an A, a B, and a C. But if I do, then I don't know what the truth value is, for example, for GA, or what the truth value is for GC. So this is not really the best way to recover an interpretation, though it certainly shows us sort of what's going on when we compare it to what's going on in sentential logic. So remember, to provide an interpretation is to provide a universe of discourse and the extensions of all the predicates and the reference of all the constants. So what we need to do here is just a little bit different. What we notice here from our completed open branch is indeed that we're going to need an A, a B, and a C. And so that right away tells us that we're going to need a universe of discourse with 3 things in it. Now, it doesn't much matter what things you put in your universe of discourse, but it's sort of convenient to use numbers. So my three things are going to be the numbers 1, 2, and 3. And then what I want to specify is my predicates. Now, I'm going to just cover up this branch here so that I can write down the predicates the way we're used to seeing them underneath the universe of discourse. So, for example, for fx, I want the extension of this predicate to include a and b, but not c. So now that means I'm going to need to say what a and b and c are. So a is going to be 1, b is going to be 2, and c is going to be 3. So now the extension of my predicate fx is going to be 1, 2, because that tells me that f of a is true and f of b is true. It tells me that 1 is an f and 1 is a, so f of a is true. It tells me that 2 is an f, so f of b is true. It also tells me that since 3 is not in the extension of f of c is false. Then I do the same thing for the predicate g. I want to write a set that shows me that GB is true. Well, to show that GB is true, what I need to do is put 2 in the extension of GX. Because what this tells me is that 2 is a G, right? But 2 is B, so in other words, GB is true. And this is the interpretation that I can recover from this truth tree to demonstrate that on this interpretation, the two original sentences at the top of the tree are both true.